Hello everyone, I hope you are doing well. Today I'm gonna discuss the basic concepts in probability and statistics. Here is the overview of this session. I'm gonna start with the definition of the variables. A variable simply means any property or descriptor that can take multiple values. For example, assume we have a study that compares the health of smokers and non-smokers. So one of the variables could be the age of participants and or the gender of the participants, maybe the family history of cancer for a certain participant, or how many years the participant has been smoking. All of them, as you can see, could take different values, and in the data science, we call these variables simply the features. Different features in the data. So another way that you can think about a variable is a variable simply is a question that when you answer that question, you may use different values, depend to the situation. For example, age is a variable in the study that we discussed in the example. So if someone asks how old is this participant and the participant answers 38, that means the value of variable age is 38 in this example. So that's another way to think about a variable. Um, Another important concept is the probability of a variable or probability distribution of a variable and the type of variables that we deal with. So later on, I will define the concept of the probability. And to show the probability of a variable, we use this notation. P of x, capital X, equals to lowercase x. That means what's the probability of variable x that takes the value of lowercase x. And sometimes, if there is no ambiguity involved, we simply write it down P of x, lowercase x. In many cases, in data science, the number of variables that we consider is more than one. So we have multiple variables, and the probability is a joint probability. So we have a joint probability, for example, here of x and y. Another thing that you need to consider is when we talk about the probability of a variable, for example, P of x equals 38, And technically, this means the probability of an individual randomly selected from the population. So I use two words here: random selection and population. In many cases, in science, we try to make conclusions that is true for the whole population that we are interested in. For example, you want to say something about the relationship between the smoking and the lung cancer in the whole population of the US. So, but as you may notice, it's not easy to study the entire population in many cases due to the costs and the time that we need to run those experiments. So what we do is usually we use some instances of a population that is called sampling. And I'm pretty sure that you read this section of the textbook about the different sampling technique. And one of the most important one is the random sampling. And why we do the random sampling? Because we want to select a set of individuals from the population that by studying that set of samples represent the whole population. So we want to have a representative sample of the whole population. Because of that, it's very important to consider a sampling technique that guarantees that the conclusions that we make about the sample also can be generalized to the population. But it's a very difficult task and it's a very subtle task that we may discuss in here or there in this course. Let's talk about different types of variables. A variable could be discrete. That means it can take one of a finite values in a range, or it could be a continuous variable. As an example, a variable that explains the state of a standard light, which is on or off, so is a discrete variable. And a variable that describes the weight of a person in a study is a continuous variable. For example, the weight of the person could be between 30 kilogram to something less than 120 kilogram in a study. Yeah. So any number in between is a valid number for the weight of a participant in this study. So that's the difference between a discrete and continuous variable. Another concept, which is very important concept before the definition of the probability of a variable is, or an event, is the sample space. And a sample space means a set of all possibilities and all possible outcomes of an experiment. For example, the sample space for possible outcomes of one flip of a coin is this set. S equals to H. H stands for head, and T stands for tail. So this sample space has only two members. So the cardinality of this sample space is 2. As another example, if an experiment consists of one roll of a die and we are interested in which face is turned up, the sample space is S equals to 1 to 6. Yeah, 1, 2, 3, 4, 5, and 6. And the cardinality of this sample space is 6 because we have 6 elements in this sample space. So here the concept that is very important is counting that you learned from discrete math. So if you forgot the different counting technique, I highly encourage you to go back and brush your memory about the combinatorics and learn how to count the number of events in a sample and be prepared for the rest of this chapter. Another concept is the event, which means the subset of a sample space. So, for example, if you roll a pair of dice, one red and one green, what would be the sample space in this scenario? And it's very simple. The sample space is a set of ordered pairs because we have two different dice. One is red. The first one is for the red die, and the second one is for the green one. And X can take the value 1 to 6, and Y can take the value from 1 to 6 as well. Yeah. So another way that you can write it down, this sample space is listing the elements. Yeah. 1 and 1, 1 and 2, all the way to 1 and 6. And you can follow this pattern. And the last row is 6 and 1, all the way to 6 and 6. In all cases, the first element shows the value for the red one, and the second element shows the value for the green one. So as you can see in this case, the cardinality of S is 6 times 6, which is 36. So assume that we are interested in an event that shows the total number of points rolled with the pair of dice, and that total number is 7. So in that case, you can see that B, the event B, has only 6 elements. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Remember that 3 and 4 is different from 4 and 3 because 3 and 4, 3 is red, 4 is green, but 4 and 3, 4 is red and 3 is green. So this event, for this event, the cardinality of B is 6 because we have 6 elements and 6 different possibilities that the sum of the pairs is 7. So we need to do this type of counting to compute the probability of an event. So the way that we can define the probability on an event is using the frequency technique, which means the probability of an event is computed as the ratio of the cardinality of the number of times that event A happens in the with respect to the sample size of the sample space. So, for example, what's the probability of drawing an ace from a well-shuffled deck of 52 playing cards? So how many aces we have in 52 playing cards is 4, yeah? So the cardinality of A is 4 divided by the number of different possibilities, which is 52 cards. So the probability of ace, so P of ace, in this example is 4 divided by 52. As another example, assume we flip a balanced coin twice. I want to compute the probability of getting at least one head. So in this case, what's the sample space? The sample space is like this, yeah? HH, head, head. That means the first one is head, the second one is head. HT, the first one is head, the second one is tail. TH, the first one is tail, the second one is H. And TT, which means the first one is tail, the second one is tail as well. So that's S. What is A in this case? Is the possibility that you get at least one head. That means at least. That means one head or more. So, which means HH, HT, and TH. So in that case, the probability of A equals to 3 divided by 4 or 0.75. There are 3 axioms about a finite sample space, about the probability of a finite sample space that is called the Kolmogorov axioms. Kolmogorov axioms. The first one is the probability of an event always is a number between 0 and 1. The probability of the entire sample space is 1. And if you have 2 mutual exclusive events in the sample space S, then the probability of A union B equals to the probability of A plus the probability of B. And if I want to visualize this part, Most likely you remember the Venn diagram, and when we have two events without any overlap, for example, A and B, and the probability A union B, so A union B is the shaded area in this Venn diagram, A union B. And as you can see, since these two events there is no overlap between them, the probability of A union B equals to P of A plus P of B. So in the case that there is an overlap between A and B, it's not difficult to see that probability of A union B equals to, so P of A union B equals to P of A plus P of B minus P of A intersection with B. And the reason is, in this case, when you compute the probability of A union B, you are computing the probability of the intersection twice. So you have to subtract one of them to compute the probability of P of A union B correctly. But when the events are mutually exclusive, the probability of A union as intersection with B is 0, because that intersection is empty, as you can see here. A intersection of B in this Venn diagram is empty. So that means the part that you're going to subtract, the probability is 0. So because the probability of S is 1, and also the probability of empty space is 0 for sure. So these three together shows the Kolmogorov axioms. And as an example, we can check it out. If someone gives us a set of probabilities and ask whether the assignment of probabilities is a valid assignment, we can answer the question by pay attention to these three axioms. For example, in case A, the answer is no, because the probability of an event cannot be negative. Yeah? And for the case B, it's not difficult to see that if A, B, and C are mutually exclusive, the sum of the union of A, the probability of union A, B, and C must be 1, which is in this case is not. It's not 1. So that means, because 0.35 plus 0.52 plus 0.26 is more than 1. So it is not going to happen. The probability always is between 0 and 1. And when the events are mutually exclusive, the sum of them cannot exceed 1. And the last example here is the probability of each event is between 0 and 1. And the probability of union of A, B, and C is 1, since A, B, and C are mutually exclusive. And since that satisfies all three axioms from Kolmogorov axioms, we can say that the part C, this part, shows a probability, a valid assignment of probabilities. Another topic is conditional probability, and there are different ways to define a conditional probability. And one way is to say, I'm going to compute the probability of event A given the case that we have event B. So in that case, the conditional probability is defined as the probability of intersection between A and B divided by probability of B. So remember that the probability of B must be non-zero because we cannot divide by 0. For example, here we have companies for car service. Some of them are in the business 10 years or more. Some of them are in the business less than 10 years. Some of them have good service. Some of them have a poor service based on reviews that we collected from the users and customers from these companies. And these are the numbers. For example, we have 16 organization or car dealers that are in the business more than 10 years, and also people say they have good services. So the first question is, what is the probability that someone gets one who provides good service under warranty if a person randomly selects one of new car dealers? So new car dealers means in this scenario, in the business less than 10 years, which is this row. I'm going to highlight with blue. So in that case, what's the probability that someone gets one who provides good service? So in this case, the number of dealers in the new dealers is 30. 10 plus 20 is 30. So that's the sample space. And only 10 of them have good services based on reviews. So that means the chance to get a good service from new dealers is 1/3. And for the second part, we want to compute the probability that a person randomly selects one of the dealers who has been in business for 10 years or more. So in this case, we consider the first row 10 years or more. And what's the probability that he gets one who provides good service? In this case, the number of dealers in the business 10 years or more is 16 plus 4, which is 20. And the number of dealers with good service 10 years or more is 16. So divided by 16 by 4 by 2 is 8. 20 by 2 is 10. So it's 8 divided by 10 is 0.8. So it's 80% chance to have a good service. So which makes sense, yeah. To have a good service for new dealers, the chance is about 30%, but the chance to have a good service with dealers, more experienced dealers, is 80%. So it's kind of reasonable. Another concept related to the conditional probability is the general multiplication rule, which means when we have P of A given B, the conditional probability is defined as P of A intersection with B divided by P of B. So if you do the cross multiplication, you get the formula for general multiplication rule of probability. So P of A intersection with B equals to P of A times P of B given A, or P of B times P of A given B. Both cases possible. Let me solve a simple example to show the how to use the general multiplication rule. It says we pick two television sets in succession from a shipment of 240 television sets that 15 of them are defective. What is the probability that they will both be defective? So, but we pick them randomly, and okay, what's the probability of the pick a random television and that television be defective? So the number of defective TVs is 15 out of 240 cases, yeah? So that's the probability of being a television defective. And the second one times the second one also is defective. We want to compute the probability of both be defective. And we know that the first one also is defective. So how many defective TVs remains? So it's 14. So you see how is related to the conditional probability. So the second probability depends to look at the first probability, yeah? So is related to the conditional probability. In the second case, we have only 14 defective TVs. Out of how many? You remember that we picked one of the TVs first, so only 239 remains for the second one. So this, if you compute this multiplication, you get the probability of both TVs be defective. And here there are a couple of assumptions that we made. And the first assumption is when we pick the TVs randomly, when I pick the first one, I do not replace the first one. So it's called sampling without replacement. That means when you pick the first one, the second one is picked from the rest of them. So you do not replace the first one in the sample space. And the second assumption is, which is hidden, I'll talk about it maybe in the coming slides, is the first and the second event are independent. So are dependent. In the second one, the probability is dependent to the probability of the first one, yeah? So because of that, we use the second one. When you compute the probability of the second case, you have to consider what happened in the first case when you pick the first television. So the next topic is the independence. We say two events are independent if P of A given B equals to P of A. That means the probability of A doesn't depend on the probability of B. So observing the behavior of B doesn't have any added value to compute the probability of A, since A is dependent of B. So knowing the state of B doesn't have anything to do with the knowing the state of A. So in that case, these two are independent. It's not difficult to show that using the general multiplication or multiplication rule of probability, that when we have P of A and P of B, if these two events are independent, so the probability of the intersection can be written as the multiplication of their probabilities. And for example, what's the probability of getting two heads in two flips of a balanced coin? So the probability of first one is 1/2, because we have only two possibilities and the coin is balanced. So 50% is for the first one. And the second one is independent from the first one. So the probability of having a head for the second flip is also 1/2. So that means 1/4. That's one way to solve this example. While we do the multiplication, P of A times P of B, we consider having head as a two separate independent events, because in this example, the probability of having head in the second flip, that doesn't depend on what happened in the first flip. As another example, I have two events, C and D. I have the probability of C and probability of D, also the probability of C intersection with D. I want to see that if C and D are independent. So based on the theorem and the definition of the two independent events, you can see that P of C times P of D, in this case, equals to 0.65 times 0.4, which is 0.26. So, and this is different from the probability of C intersection with D. That means C and D are not independent. C and D are dependent. The next example says, what is the probability of not rolling any 6 in 4 rolls of a balanced die? So every time that you roll this die, the outcome is independent from the previous roll. So that means you can use the independence of the events and the probability of not having 4, not having 6 is 5/6 to the power of 4. 4 times you repeat this event, yeah? So 5/6 for the first one, 5/6 for the second one, 5/6 for the third one, and 5/6 for the fourth one. And each one of them are independent of the others. So you can use a multiplication technique to compute the probability of this scenario, this event. Another concept is probability distribution. Technically, the probability of an event, we learn how to compute the probability of an event when we know the event and the sample space. But when we have a sample space and our random variable takes different values, for different input values, you may take different probability output, yeah? So for example, in a rolling a die, we have 6 different inputs, yeah? So you can think about the probability as a function. So if you remember from discrete math or calculus course, a function maps the inputs value, the input values to the output values. And probability of a discrete random variable x that takes the value of lowercase x, you can think about it as a function that maps this x to a number between 0 and 1. Yeah? You remember that based on the Kolmogorov's axioms, this is a number between 0 and 1. So when we have a probability distribution, this function is always non-negative. It's always returns a number 0 or bigger than 0, and the summation of, in the discrete case, the summation of f of x for all x's equals to 1. As an example, we want to check that if this function defines the probability distribution for this random variable x. So you can easily check that f of x always is 0 or bigger than 0. If you substitute x with 0, you get 0. And if you substitute x with 1, 2, 3, or 4, definitely you get a positive number. So that's the first condition is satisfied. I want to check the second condition. What's the summation of f of x when x changes from 0 to 4? So that means 0 plus 1 squared is 1 divided by 25 plus 2 squared divided by 25 plus 3 squared divided by 25 plus 4 squared divided by 25. If I simplify this summation, that means the numerator is 25 and the numerator is 1 plus 4 plus 6 plus 16 plus 9 plus 16. Which is 10 plus 20 is 30 divided by 25. And obviously this number is bigger than 1. So it doesn't satisfy the second one. So the second rule is not satisfied. So I cannot say that this function shows a probability distribution. But the second one, B, also is not a probability distribution, because if I substitute x at 1, h of 1 is 1 minus 2 divided by 2, which is negative 1/2. The probability cannot be less than 0. So this one also is not a probability distribution. But for example, can I give you a situation that the function defines a probability distribution? For example, the case that you roll a die, f of x, if the die is balanced, is 1/6. Doesn't matter what is x. Yeah, x is 1 or 2 or 6. Any number between 1 and 6, if the die is balanced, the function returns 1/6. And if you remember, this type of function is called constant function. Constant. There are different distributions discussed in the textbook: Bernoulli distribution, binomial distribution, and Gaussian distribution. And we will discuss these three types of distributions in the next session. And I'm going to explain a couple of important laws and properties regarding the probability distributions. And the first one is the law of total probability. And this is a situation that your sample space is partitioned to several subspaces. For example, here, assume we have a subspace B1, subspace B2, and subspace B3. We call this a partition because S is divided in a special way. First of all, any of BI's for any I is not empty. There is no overlap between subspaces. So for any I and J, BI intersection with BJ is empty. And the union of BI's is the whole sample space. So a partition must satisfy all these conditions. And assume you have an event in this space, like A, and I'm going to compute the probability of A. As you can see, part of A is in the subspace B1, part of A is in the subspace B2, and part of A is in the subspace B3. So the probability of A is divided in 3 different subspaces. So the formula is like this. And the way that you can understand this formula is using the tree diagram. So we have 3 subspaces, B1, B2, and B3. So we have 3 branches. Each branch represents a subspace. And as you can see, to compute the probability of A, you have to consider the probability of A based on the probability of A in a different subspaces And in that case, you are going to multiply the probability of that subspace with the probability of A in that subspace. So, and when you do this, the probability of A is the summation of all these multiplication. P of B1 times P of A given B1, P of B2 times P of B2 times P of A given B2, and P of B3 times P of A given B3. So that's the way that you can write it down, the total probability of A. Let me give you a concrete example in the next slide. We have 3 rental car companies, and so we have 3 agencies. I'm going to use 3 branches. The probability of agency 1 is 0.6 because 60% of cars are coming from agency 1. Probability of agency 2 is 0.3 because only 30% of rental cars coming from agency 2, and the probability of A3 is 0.1, which is only 10% of cars are coming from agency 3. The main thing is in case in the case that you ordered a rental car or booked a rental car and only 9% of the cars from agency 1 need an oil change. So the main thing is oil change here, the main problem. So P of oil change, need an oil change, in the case that is coming from agency 1 is 0.09. The probability of to need an oil change if the car is coming from agency 2 is 20%, which means 0.2, and the probability of need an oil change when the car is coming from agency 3 is 6%, which means 0.06. And the total probability is, if I want to compute the probability of what's the probability of a rental car delivered to the firm, will need an oil change. So probability of oil change is 0.6 times 0.09 plus 0.3 times 0.2 plus 0.1 times 0.06. That's the total probability. This summation, the whole summation gives you the total probability of a delivered car needs an oil change. So you're ready to define another rule, which is very important in statistics and also in the data science course, is Bayes rule. The Bayes rule is to the way that you can compute the probability of a subclass given that event. So in our example, I'm going to compute what would be the probability of the case that the car belongs to agency 2 if I know that the car needs an oil change. Yeah. So this kind of probability is called the Bayes rule. So to compute the Bayes rule, the probability of a subclass given the event is very simple. You compute the total probability in the denominator. P of A is your denominator, and the numerator is the probability that you compute only for the branch of interest. Yeah. For example, here, if you want to compute what's the probability of agency 2, if we know that the car needs an oil change, so you only compute the probability of A2 times probability of needing an oil change given A2 divided by P of oil change. So the numerator is only for the branch that we are interested in. And we are going to compute the probability of that subspace. So let me solve a solid example to show you how to use the Bayes rule. So I'm going to compute what's the probability that if the car came from a rental car agency A2, if the car needs an oil change. Yeah. So we discussed how to compute the total probability. That's the denominator of this fraction. The numerator is the probability of A2 times the probability of needs an oil change given A2. So which is the numerator is, what was the probability of agency 2? I believe was 0.3. And how many of them needed oil change? I believe it was 20%, which is 0.3 times 0.2. The next topic is expected values, or another name for it is mean, or that the simple for mean or average. These are different names for expected values, is mu. So mu is the symbol for the expected value. Let me explain it with a simple example. Assume you flip a balance coin 100 times. How many times you expect to have a tail? So you flip the coin 100 times, and each time the chance is 1/2. So you expect to have 50 times to see 50 tails in the case that you flip a balance coin 100 times. If I generalize this idea, the expected value of a variable is the summation of the number of times that event happened times the probability of that event. and you sum them up, that gives you the expected value of x. E of x, expected value, E stands for expected value. And sometimes we simply shows it with mu. Let me give you a simple example. I roll a dice twice. You see that in the table. And the first roll is for x. For example, this is the value for x. And the second is for the y variable. I'm going to compute the max of x and y as your z variable. Yeah. So if the first one is 1 and the second one is 1, the maximum is 1. If the first one is 1, the second one is 2, the maximum is 2. If the first one is 1, the second one is 3, the maximum is 3. If the first one is 1, the second one is 4, the maximum is 4. If the first one is 1, the second one is 5, the maximum is 5. And for example, this one, if the first one is 4 and the second one is 4, the maximum is 4. If the second one is 5, the second one is 3, the maximum is 5. So I want to compute the expectation of this random variable. Okay, so I need to compute the probabilities for this random variable z first. So what are the values for this random variable z? So you see that the maximum number are between 1, 2, 3, 4, 5, and 6. What's the probability of the maximum is 1? Only in one case, the maximum is 1. So the probability is 1 over 36. How many times we have 2 as the maximum value of x and y? 3 times. So 3 over 36. How many times we have 3? You see that? We have 5 cases that the maximum number is 3. How many 4s we have? 1, 2, 3, 4, 5, 6, 7. How many 5s? 9. How many 6s? 11. So in this case, based on the formula that you see here, you can compute the expected value of z, which is the summation of z times p of z or f of z. Let's call this f of z, z times f of z, z from 1 to 6. So that means 1 times 1 over 36 plus 2 times 3 over 36 plus 3 times 5 over 36 plus 4 times 7 over 36 plus 5 times 9 over 36 plus 6 times 11 over 36. And if you sum them all, you get the expected value for z. Another important concept is the variance, which means how much the random variable x varies in the range of x values, and simply means you subtract the value of x and mean, and you compute the square of that subtraction multiplied by f of x. So the idea is similar to the mean, but instead of x times f of x, you compute the x minus mu squared times f of x. Why x minus mu squared? Because if you do not square the subtraction, the positive and negative numbers cancel out each other, and this value becomes 0. So to have a meaningful metric to shows the range of changes in the random variable, we need to square this subtraction. So let me show you with a simple example how to compute the variance of a random variable. In this case, the random variable represents the number of points rolled with a balanced die. So the sample space is 1, 2, 3, 4, 5, and 6. And I'm going to compute the mu first because I need the value of the mean. So mu is sigma x times f of x. That's the mean of the random variable x. In this case, if you remember, f of x was 1 over 6 for any x. So 1 over 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. 1 plus 2, 3 plus 3, 6 plus 4, 10, 15 plus 6, 21. 21 divided by 6. You can divide it by 3. 7 divided by 2, which is 3.5. So the mean of this random variable is 3.5. So if you want to compute the variance of x in this example, the answer is 1 minus 3.5 squared times f of x times 1 over 6 plus 2 minus 3.5 squared times 1 over 6 plus 3 minus 3.5 squared times 1 over 6 plus 4 minus 3.5 squared times 1 over 6 plus 5 minus 3.7 squared times 1 over 6 plus 6 minus 3.5 squared times 1 over 6. If you simplify this numbers, multiplications, and additions, at the end, you get the variance of this variable. And if you compute the squared root squared of this number, you get the standard variation. So variance, expected value, and a standard deviation. A standard deviation are three metrics that we use to do some statistical analysis in this course. We will explain the probability distributions and some rules about the inference in statistics in the next sessions. Thank you very much.